Slight
No, sir.
changing?
No, sir. No, sir. It's still in the objectives of wastewater treatment.
Okay.
Share entire screen and then go to
Okay.
slideshow.
Okay. Is it okay now?
Yes, sir. Yes, sir. Yes, sir.
Okay. Session 1 from up to 11:30. So we have advanced water and wastewater treatment techniques. So first we see the water treatment techniques. So then we move to the advanced water treatment techniques are available. Same way we will see about the wastewater treatment, that is sewage treatment, and the various methods available to treat the sewage by the advanced wastewater treatment techniques. So this is the flow of my presentation. So first we see the water treatment. So we know that the objectives of water treatment is to supply the consumer with safe and clean water. So therefore, we have to remove the impurities from the raw water, which is get from the any kind of sources like lake, river, pond, or any kind of underground water. So the main aim is to convert the water into safe and clean, and also we have to what extent we have to treat the water is to meet the water quality standards. So these are all the prime objective of water treatment. So the impurities. So these are all the impurities we can classify under physical, chemical, and biological. So turbidity, temperature, color, odor, taste. So these are all some of the physical impurities. Under the chemical, yes, we have pH, hardness, fluoride, iron and manganese, nitrates, and any kind of solids and toxic substances. In the same way, we need to convert the water into safe. So we have to kill all the pathogens like bacteria, virus, and other plants also, so microplants. So for that, so we go for the disinfection. Here I have given some important drinking water standards like turbidity. So the acceptable limit is 1 NTU. It should not greater than 5. We can use up to 5 if no other water is available. Yes, we go up to 5 NTU. So nephrometric turbidity units. And pH it should be from 6.5 to 8.5. So there is no lesser value or higher than the 8.5. So it should be within this 6.5 and 8.5. So TDS is the total dissolved solids. We can say in another name like hardness. Okay, so we can have up to 500 milligram per liter. Then the rejection limit 2000. Then fluoride 1 and 1.5 is the rejection limit. So likewise, iron content 0.3 milligram per liter, manganese 0.05 milligram per liter, nitrate 45 milligram per liter. Then the E. coli, that is coliform, it's a kind of indicator organism which is present in our intestine. So if there is any bacterial contamination, so it should be nil in our drinking water. Okay. So for that only we go for the disinfection. So these are all classified the different impurities based on its physical, chemical, and biological characteristics. We simply say in the form of solids, yes, the raw water contains floatable solids. Yes, whenever we see any kind of lake water or pond water or river water, so the a person, okay, which is not having any kind of knowledge, can easily identify the water is contaminated or what kind of things are present in the raw water. Okay, so therefore, in the form of solids, so the raw water contains floatable solids. Yes, a lot of any plastic cloths or any leaves, branches, whatever the things floating in the water. Yes, those kind of impurities are called floating solids. Then we have the suspended. Suspended means we can see the solids using our naked eyes. Okay, so those kind of solids is called suspended solids. So in that particular suspended solids, we have a settlable and non-settlable. So no issue to remove the settlable solids. It's also called discrete. Okay, whenever we retard the flow, the solids, there is the discrete solids present in the raw water is immediately settled down. But the problem creating the solid in the form of suspended is colloidal solids. So because it have a electrically charged, that is negatively charged particles, so it cannot settle down because all the negatively charged particles are reflecting each other. So therefore, it cannot settle down. Even we have store more than a month or a year. Okay, so these kind of solids are creating a problem during the treatment. So therefore, whatever we are going to see is mainly for the colloidal. Once we neutralize this colloidal, yes, all the other things can happen, no issues. Okay, so in our like conventional water treatment, like metro water or any kind of water supplied by the corporation or municipality or from the any agencies to the general public, so we go for up to the suspended solids removal. So we are not bothered about the dissolved salts. Mostly our surface water in Tamil Nadu, okay, have the TDS is less than the 500 or the desirable limit of 300. Okay, so we are not much concentrate on the treatment of dissolved solids. I'm talking about the conventional way of treating water. So we are going to see the advanced water treatment to treat the dissolved solids. But for the conventional treatment, that is the water treated and supplied to the consumer, we go up to the removal of suspended solids. Then under dissolved solids, all the chemical substances like the chemical characteristics, hardness, iron and manganese, fluoride. So everything comes under the dissolved solids, so which we cannot see our naked eye. So first we see the some of the conventional treatment, then we move to the advanced one. So for the floatable solids removal, yes, we have the unit, treatment unit like screen chamber. The processes or the operation is screening. Okay, screening can be used to remove the floatable solids. Yes, for the readily settlable, yes, sedimentation and filtration is alone enough, but the colloidal solids creates problem. Okay, so therefore we go for the coagulation, flocculation. Then we move to the sedimentation and filtration process. So briefly, I will explain the coagulation, flocculation, clarification, as well as the filtration process. Then for the dissolved substances, yes, we go for the water softening, or to convert the saline water or seawater to the distilled quality. Yes, we go for reverse osmosis or a thermal desalination process. So these are all the methods available to remove the various types of solids. Yes, we can say the entire treatment processes or types of treatments comes under unit operation and process. The contaminants removed by the physical force, using the physical forces, means that particular treatment is called unit operation. in other way. Okay, so if we use any chemical or biological treatment to treat the or to remove the contaminants, yes, that particular treatment units are called unit processes. So mostly the conventional treatments are based on the unit operation, like screening, sedimentation, filtration. But the coagulation, flocculation, disinfections comes under the unit processes. Then all the advanced water treatment processes like ion exchange process or demineralization process. So those kind of things we are adding, or we are using some kind of chemicals. So therefore, those things comes under the unit processes. So in this particular table, I have given the different impurities and the unit operation processes involved to remove those impurities. So for the removal of floatable debris or any kind of fish or other living things, okay, so we have the coarse screen. So mostly these kind of coarse screens are provided at the intake structure, which is available at our sources. Okay, so next, because of a lot of organic matters available in our raw water, so the decomposition is happening. So because of that, the water contains a lot of organic gases. So those kind of gases can be removed, or we can increase the dissolved oxygen by aeration. Then for the mixing of coagulants, yes, that is aluminum sulfate, is we can call it as a coagulation process. So it is a rapid mixing process. So at the end of this rapid mixing, that is, we are thoroughly mixing the coagulant into the raw water. So why we are adding coagulant means, yes, the colloidal solids creating problem. So it is a negatively charged particles. So therefore, we are adding the positively charged aluminum sulfate. Okay, so aluminum is a positively charged metal. So we are adding the metal salt to neutralize the colloidal solids. So first we are adding the coagulant into the raw water, and we are doing a thorough mixing. So thorough dispersion of aluminum alum into the raw water. So at the end of the coagulation process, so all the colloidal solids are neutralized, and it will form a microflux. Then during the flocculation process, so it is a slow mixing process. So around 2 to 3 RPM, up to half an hour, we go for a flocculation process. For a rapid mixing, that is for coagulation, we go for up to 100 to 200 RPM for 2 to 3 minutes. So during the flocculation process, so all the microflux are attached together, and it will form a macroflux or readily settlable. These kind of macroflux are readily settlable along with discrete solids. So already the raw water contains discrete solids also. Discrete means it is a very high specific gravity, more than the water. So it is readily settlable when we stop the flow. So once we achieve or we convert all the colloidal solids into macroflux, yes, next we move to the sedimentation process, where we can settle down all the discrete as well as flocculent solids or flocks. So not we can't settle down the entire settlable solids in a particular settling tank alone. So therefore, if any kind of suspended solids escapes from the sedimentation tank, yes, we can filter in the sand filters. Okay, so we are using a sand filter to filter the remaining suspended solids present in the clarified water. Okay, so finally, after the filtration, the water is clean, but the question is the water is safe or not? Okay, so ensure that the safety of the consumption. Okay, yes, we go for the disinfection. So one of the cheapest way of disinfecting the water is chlorine, that is chlorination process. Then suppose we need water with more quality, or industrial feed water, or I need a RO treated water. Okay, I have to reduce the TDS also. So dissolved solids content. So for that, we have a lot of methods are available. I have given here two methods: demineralization. Okay, so anion and cation exchange process can be used, or anion and cation exchange filter beds are used to exchange the various kind of salts or hardness. Or nowadays we are using a reverse osmosis process. So reverse osmosis is a semi-permeable membrane. Okay, it allows water alone when we apply the pressure from the higher concentration side to the lower concentration side. Yes, we are getting this semi-permeable membrane allows only the water, not any kind of a salt or a solids. So therefore, we get a very high pure water using the reverse osmosis process. So these are all some of the unit operation processes involved in the water treatment. Here I have given the flow diagram of conventional surface water treatment. So water from the source, we are taking the water from the source using the intake structure. Then through the conveyance system, yes, it reaches the treatment plant. So in the treatment plant, we have the coagulation process and the flocculation process, and sedimentation, filtration, and disinfection, and it is ready to supply to the consumer through the water distribution system. So in this sedimentation tank, we have a lot of advancement are there, like a clariflocculator or a tube settler or pulsator clarifier. So we are eliminating the coagulation and the flocculation, a separate tank for coagulation flocculation. We are establishing these kind of coagulation, flocculation, sedimentation in a single tank. So the best example for this kind of sedimentation basin is pulsator clarifier, which is available in Sriperumbudur water treatment plant. In the same way, so we have the sand filters. So based on the rate of filtration, so we have a slow sand filter, rapid sand filter, and pressure sand filters. So in most of the water treatment plants, we have the rapid sand filtration, and a small kind of rainwater harvesting system. So we have a pressure sand filter systems. So one of the technology in the sedimentation basin, which is available in Sriperumbudur water treatment plant, is pulsator clarifier. So here, all the three process, coagulation, flocculation, and sedimentation is happening in a single tank. Okay, so the raw water, so the raw water enter through this inlet pipe. So at the pipe itself, we are introducing the coagulant, that is aluminum sulfate, and which is introduced in the central chamber, which is located. It is also called vacuum chamber. So here, the raw water along with the alum is introduced. Here, using the vacuum pump, we are creating the vacuum. So because of the vacuum, so the water level get raised up to the top. So once it reaches the top, okay, the vacuum brake valve breaks the vacuum. So because of that, the water is moving towards the bottom with high speed. So during that particular process, the entire alum is thoroughly mixed with the raw water. So therefore, the coagulation process is happening here. Then it reaches through this perforated pipe. So here we have the perforated pipe is the exit to the clarification location. It also contains the sludge bed. So in this particular sludge bed, I already said during the coagulation process, the microflux are formed. So once it reaches the bottom of this tank, the velocity gets reduced and the microflux are converted as a macroflux. These macroflux are stopped by this sludge bed. Okay, so the entire sludges are accumulated at the bottom. The clarified water, that is the water free from the colloidal or discrete particle, will move to the next process called sand filter. Okay. So whenever we are creating the vacuum, there is a compression is happening in this sludge zone, and whenever we are releasing, here there is an expansion is happening. So because of the expansion, the already settled excess sludge are disposed through the sludge removal. Okay, so therefore the coagulation process, flocculation, and settling. So entire thing is happening in a single tank. So now we move to the advanced water treatment. So mainly for the removal of dissolved solids. So now we are going to see the water softening, then what are all the methods available to convert the hard water to soft water, then desalination process, then fluoride removal system. So we'll see one by one. So first, water softening. So during the conventional treatment, we are removing only the suspended solids present in the raw water. So for the domestic use, that particular conventional treatment alone is enough. But for the industrial feed water, or we have to improve the quality of the water based on our requirements, yes, we go for the advanced water treatment. So in that, first one is the water softening, that is the removal of hardness from the water. So we know that, yes, hardness is classified as temporary hardness, that is carbonate hardness. And permanent hardness is also called non-carbonate hardness. So carbonate and bicarbonates of calcium and magnesium impart the temporary hardness into the water. Yes, for the carbonate temporary hardness we can remove using the boiling alone. Yes, so during this boiling, okay, so calcium carbonate or calcium bicarbonate, that is, it is in the dissolved state. Okay, so dissolved state calcium bicarbonate is converted into insoluble precipitate like calcium carbonate, then CO2 gas get released. Okay. And magnesium also, but so we can't remove the magnesium carbonate by boiling alone. So therefore we go for the lime process. So adding lime, boiling and adding lime can easily remove the magnesium carbonate or temporary hardness. So here the magnesium carbonate react with the lime calcium hydroxide, then it will convert the magnesium into magnesium hydroxide precipitate and a calcium carbonate precipitate. So like this, like that, we can convert magnesium bicarbonate into calcium bicarbonate and calcium bicarbonate into calcium carbonate precipitate. So this is the way we can remove the temporary hardness. Then permanent hardness means, so it is mainly due to the presence of the sulfate, chloride, and nitrates of calcium, magnesium, ferrous, and manganese. Okay, so calcium chloride, calcium sulfate, magnesium chloride, magnesium sulfate, or ferric chloride, so ferrous sulfate. So these are all the permanent hardness. We can't remove using boiling or just adding the lime alone. So so for the removal of the permanent hardness, yes, along with the lime, we have to add soda also. So therefore, it is called a lime soda process. Then we have the zeolite process and demineralization process are available to remove the permanent hardness from the water. So first we see the lime soda process. So these are all the temporary as well as the permanent hardness. First we are adding the lime, okay, or first it react with the lime, okay. So all these the temporary hardness are converted as a calcium carbonate precipitate, but some of the magnesium permanent hardness are converted into non-carbonate calcium hardness. Then this calcium permanent hardness is react with the sodium carbonate, that is soda. It will convert into calcium carbonate precipitate. Okay, so therefore all the calcium carbonate and bicarbonates are removed using the lime alone, but the magnesium chloride and magnesium sulfate, so these things cannot be removed using lime alone. So during the addition of lime, this magnesium carbonates are converted into calcium hardness. Then this calcium hardness is converted as a calcium carbonate by adding the soda. So after this hardness removal process, the precipitate, calcium carbonate precipitate are developed. So these calcium carbonate precipitates are settled down during the filtration process. After the filtration, so we have some residual precipitation of calcium carbonates are available. So to convert those insoluble precipitate into soluble calcium carbonate into the treated water by introducing carbon dioxide. That is, we have to do the recarbonation process to convert entire insoluble calcium carbonate into soluble bicarbonates. So next, so using this lime soda process, we can't achieve the 100% removal of hardness. We can achieve up to 50 milligram per liter of hardness only. But using the zeolite or any this kind of a base exchange method, we can achieve up to 0% hardness. So zeolite is a natural salt, or we can artificially make the zeolite as a zeolite resins. So we can use this zeolite as a filter bed, like this picture. So this is a zeolite bed supported by the gravel layer, like our pressure sand filter. Okay, so we are introducing hard water from the top. So in this zeolite bed, is remove, that is sodium zeolite. So removes or converts or replaced all the calcium and magnesium salt into calcium magnesium zeolite and sodium carbonate, sulfate, and chloride salts. These kind of a salts not comes under the hardness, or which is does not create any hardness. Okay, so here also we can regenerate this used zeolite using the 5 to 10% sodium chloride solution. So therefore, uh, we can't waste the used zeolite like activated carbon. So we can regenerate the zeolite. Again, we can use it to remove the hardness by washing the used zeolite by sodium chloride 10% up to 10% brine solution, that is sodium chloride solution. Okay. Yes, we can achieve up to zero hardness. Okay, in the lime soda process, yes, we are creating heavy load on the filtration process, but here the sludge is very less. Okay, so therefore it doesn't create any load on the filtration process. So next we move to the demineralization process. Okay, so in this particular treatment, yes, we are having these two kind of filter beds. So cation exchange filter bed and anion exchange beds. So cation exchange bed replaces the cations present in the water, as well as the anion exchanger exchanges the anions. So first, we are introducing the hard water into the cation exchange bed. Here, these are all the reaction happening. So here we have the hardness, introducing it into the cation exchange resin bed. Okay, so here all the calcium, magnesium, and the sodium salts are replaced with the hydrogen, and it forms diluted acids. Then this diluted acid is introduced into the anion exchange bed. So here all the negatively charged like chlorine or sulfate ions are replaced by this anion exchange resin. Finally, we get the treated water. Here also we can regenerate the used resins using the same acid and alkaline solution. So cation exchange resins are regenerated using the acid solution. Then the anion exchange resins are regenerated using the base alkaline solution. So next we move to the desalination process. Here also we are using some of the advanced technologies to convert the seawater into the drinkable or distilled water. So we can do the salt removal by thermal desalination and membrane processes. So in the membrane process, thermal process, we are boiling the seawater. That is, we are converting the water into water vapors. Then we are condensing the water vapors after the demister. Okay, so the condensed water is a good quality distilled water. So here we have a lot of techniques or methods are available like multi-stage flash, multiple effect distillation, so vapor compression, and then low temperature evaporation techniques to convert the seawater into the distilled water. Okay. Yes, the seawater desalination process, the thermal process account for around 55%. So remaining part is that is 55% of distilled water, that is conversion of seawater into distilled water done by thermal desalination, and the remaining portion we are converting it into any kind of a membrane process. Even that membrane process, yes, we are utilizing the reverse osmosis process, one of the proven technique to convert the seawater into distilled water or potable water. So in this multi-stage flash process, yes, the seawater is heated using the steam. Then we are introducing the heated seawater into the flash chamber. Here, because of the temperature between 90 to 120 degrees Celsius, yes, the water converted as a water vapors. Okay, so these water vapors are condensed by the inlet seawater alone. So we are achieving condensation as well as we are transferring the heat. That is, we are heating the seawater enter into this process, as well as it is acting as a cooling surface to convert the water vapors into the condensed water. So finally, we get a distilled quality water. In the multi-stage, we are doing this process. Therefore, it is called multi-stage flash process. In the same way, multi-effect is here also. So we have the multiple chambers with the seawater. We are introducing the low pressure steam. So from the heat from the low pressure steam is transferred to the seawater. Then water is seawater from the seawater. The water vapors are generated. Then these water vapors are cooled by the next chamber seawater. So the water vapors are condensed into water, as well as the heat from this water vapor is transferred to the seawater. So it is happening in a multiple chambers. So therefore, it is called multi-effect distillation. Okay, so here also the two things are happening. The same seawater is acting as a coolant, and the heat from the water vapor is transferred to the seawater. Okay. Then electrodialysis. So we are using electrical charges to separate the ions present in the seawater. Okay. So here also we are providing the opposite charged semi-permeable membrane alternatively in the particular chamber. Here, this semi-membrane it allows only the opposite charged ions alone through this membrane. Okay, so it doesn't allow the water to pass through it. It allows only the ions. Because of that, yes, the central chamber have the clear water. So that is dilute. We are getting the water that is the distilled that is ions separated water from the center. So these things are happening when we introducing the electrical charge on both side, anode and cathode. So next we have the reverse osmosis. So before seeing the reverse osmosis, yes, we have to see some of the membrane processes available to treat the water or to treat the wastewater also, or the reuse of wastewater. So here we have the microfiltration, ultrafiltration, nanofiltration, reverse osmosis. So based on the pore size, these membrane processes are classified. So see this diagram. Yes, so up to 10 power minus 3 micron meter pore size we have in the RO membrane. So therefore, it allows only the water. It even it doesn't allow the monovalent ion also. So the pore size is very, very minimum compared to all other filtration process. That is 10 power minus 4 to 10 power minus 3 micron meter. Then for nano filtration, we have 10 power minus 3 to 10 power minus 2 micron meter pore size. Then the same way, okay, ultra filtration 10 power minus 2 minus 1, and micro is 10 power minus 1 to 1 micron meter. Then we have the pore size of sand filter also. So 10 to 100 micron meters. So this is how we are classifying, or we are developing the membrane processes. So in all these kind of semi-permeable membrane process, we are using the pressure. Okay, so by applying this kind of this level of pressure alone, we can obtain the filtration process. So here for the reverse osmosis, yes, we have to apply up to 8,400 kilopascal to achieve the filtration. So in this, we see the reverse osmosis process alone. Yes, reverse osmosis process is a kind of membrane process. What is happening means it is a kind of a filter only, but it is a semi-permeable membrane. It allows the water alone pass through that particular membrane. It doesn't allow any kind of a salt and the size more than the monovalent ion also. Okay. Yes, we know that when we have the membrane separated by two different kind of a concentration level, the chemical is passing through the lower concentration side to higher concentration side during the osmotic pressure. Here in this reverse osmosis, we are reversing the osmotic pressure. That is, we are applying the pressure in the higher concentration side. So because of that, the high applying pressure, the water is passing from the higher concentration side to the lower concentration side. That is, water alone is passing. See this figure. Okay, so we are applying pressure on the higher concentration side. This is a semi-permeable membrane. Okay, so because of the pore size is 10 power minus 3 micron meter. So therefore, it doesn't allow even a monovalent ion also. So the monovalent ion is bigger than the pore size of the semi-permeable membrane we used here. So therefore, we are achieving, or we are getting the water alone after the reverse osmosis. So here I have given all the impurities which is present in the raw water. So here they have given some colloidal matters also. So the entire thing is filtered here. But for the reverse osmosis, the feed water should be free from any kind of suspended impurities. So for that only in our in our house RO filter also, we have the pre-filters outside the filter unit to remove all the sediment, suspended solids, as well as any kind of organic colloidal solids also removed during the pre-carbon process. So the feed water is free from suspended solids. Then only we can use the membrane for a longer lifespan. Then removal of iron and manganese also comes under the advanced water treatment. So yes, these kind of iron and manganese are mostly present in the groundwater. in soluble state. Once it reaches the atmosphere and contact with the air, so all the ferrous insoluble soluble state of ferrous and manganese are converted into ferric and manganic insoluble salt. This creates a lot of sediments in our overhead tank or underground sump or in our pipes, that is incrustation of pipes, as well as the staining effect also it gives all our utensils, cloths. So therefore, because of iron and manganese, not much issue regarding the health, but these kind of effects, incrustation of pipe or a lot of sediments in the underground and overhead sump and staining of all our utensils, cloths, everything. So we should remove the iron and manganese from the groundwater. Okay. So the permissible limit for iron is 0.3 milligram per liter. That is drinking water standards, 0.3 milligram per liter, and for manganese it is 0.05 milligram per liter. So for the iron and manganese removal, we do a simple aeration and filtration process is enough. So anyway, during the conventional treatment, we are doing this aeration and filtration process. But in our regular residential buildings or in of industries, we are not doing any aeration and that is oxidation or filtration process. If the concentration of iron and manganese is very high, yes, we have to go for the oxidation process as well as filtration process for the removal of iron and manganese. Then another important thing is because of iron and manganese present in the water, the iron and manganese bacteria will grow in our storage tanks. So like our flushing tanks, okay, we can see the growth of iron and manganic bacteria. Okay. So because of that also, so we need to remove the iron and manganese from the water. Yes, this kind of growth, bacterial growth is happening, and this kind of incrustation is happening in our pipe. This kind of staining is happening. Yes, so here we have the iron bacteria growth in our flushing tank. So brownish color is for iron, and this kind of brown or dark black, brown to black. The reason is manganese, high level of manganese concentration. Is mainly oxidation process and the filtration process are used to remove the both ferrous and manganese. So these are all the oxidants we can use. So chlorine dioxide, potassium permanganate, and ozone can be used, or simply we do the aeration alone uh, is enough to convert the soluble ferrous and manganese into insoluble ferric and manganic salt. Then we go for the filtration to filter this insoluble matter of iron and manganese. Or we can use this zeolite process also. So manganese zeolite can be, that is green sand, can be used as a filter bed in our zeolite process. It also removes the iron and manganese from the water. So next we move to the fluoride removal. So defluoridation. So in our potable or drinking water should contain fluoride, but it should be within 1 to 1.5. If the concentration is very less or less than 1 or higher than 1.5, creates a lot of these kind of spotting or discoloration of our teeth, then gastroenteritis, skin irritation, or skeletal fluorosis or dental fluorosis. So these kind of irregular shape or staining, or even our bone also changes its shape because of high concentration of fluoride. So therefore, we should remove the fluoride from the water. So for the removal of fluoride, so we have adsorption by activated alumina. It is called Prashanti technique, or we go for any base exchange process, or we go for Nalgonda technique, or reverse osmosis. Anyway, reverse osmosis removes any kind of impurities from the water. So therefore, we go for reverse osmosis also. But for the domestic water treatment, yes, one of the proven technique is Nalgonda technique. We are not spending much amount for this particular technique. The conventional treatment alone is enough to reduce the fluoride content. That is, anyway, we are removing the colloidal solids from the water. So during the removal of colloidal, we are adding alum. So along with the alum, so we just add the lime. So along with the alum, we can add or we can include the lime also. This improves the coagulation process, as well as it reduces the fluoride concentration. So instead of activated carbon as in the filter bed, like a zeolite or a demineralization tank, so in that we have a activated alumina as a filter media. So we pass the water through this filter media. Yes, the fluoride level get reduced. Okay. So activated oxide or bone char or activated carbon also we can use for this purpose. Here also we can regenerate this activated oxide. So one of the cheapest technique developed by the NERI, National Environmental Engineering Research Institute. So in the year 1974 is the Nalgonda technique. Yes, it's a regular conventional treatment only. So here we are adding alum. So along with the alum, we are adding a lime also. This lime also reduces the hardness also. Okay, all the other treatments are same as our conventional treatment, like flocculation, sedimentation, filtration, disinfection. Then the treated water is supplied to the consumer. So now we move to the advanced wastewater treatment techniques. So first I introduce why we go for the wastewater treatment or wastewater disposal as well. Yes. So the main objective of sewage collection, treatment, and disposal is to maintain a good sanitary condition in our city, to protect our public health, then to dispose our human excreta safely, as well as we have to dispose the whatever the waste in the form of liquid can be disposed properly to avoid any kind of fly breeding or mosquito breeding or bacterial growth. Okay, so these kind of things only, these are all the things are acting as a diseases producing vector. So therefore, the liquid waste generated from our community is properly disposed, and we should treat to achieve the disposal standards based on the disposal facility developed by the BAS. Okay, so based on the disposal facility, kind of a river or a lake or any other groundwater recharge. So based on that, we have the different standards. So based on the standards, we have to treat before disposing it. So the same way, okay, so before disposing the sewage or wastewater from the domestic use, so we should treat. So for the treatment, for the selection of a particular type of a treatment or treatment methods, we need to know the exact characteristics of the sewage. So like water, raw water, so we have the physical, chemical and biological or bacteriological characteristics of sewage. So turbidity, color, odor, temperature, so are the physical characteristics. Then chemical, we have solids, pH, chloride, nitrogen, phosphate, then fat, oil and grease, and sulfates, sulfides, then DO, then BOD and COD. Okay, so in this, among these things, at least we need to concentrate or measure the BOD, COD, nitrogen, phosphate, and solids, because already we have classified, or we can classify the impurities based on the type of solids. Here also we can classify the solids present in the sewage, because 99.9% the sewage contains only the water. The 0.1% is the solids. So the 0.1% solid creates the issue here. So 0.1% solid removal is our aim also. Once we removed the 0.1% or removed or treated the 0.1% solids from the sewage is a good source of water. So far, we are not using our domestic reuse, but some of the industries, they are getting the water from our Chennai Corporation, and they are treating and they are using it for their manufacturing purpose. So one example is CPCL, they are doing that work. So therefore, that 0.1% solids creates a problem. So among these 0.1% solids, okay, 70% is the organic and 30% is the inorganic solids. Even we can't, yes, in this organic matters is, we are not bothered about this organic 30% of the organic matter. Our main thing is this organic 70% of the organic matters removal. So this creates a problem. So we have to adopt all the biological treatment units for this 70%, 0.1% solids only. In that 70% is the organic. So for this organic removal only, we go for all the treatment facilities, that is biological treatment facilities. So in the sewage treatment, yes, we can classify as a primary treatment, that is preliminary, primary and secondary treatment. But in general, the screening, grid chamber and primary clarifier, these three units are comes under the primary treatment. So therefore, the objective of the primary treatment is to remove the heavily settlable organic and inorganic solids. So heavily settlable organic and inorganic. So here we are removing the settlable organic also. Therefore, around 15 to 30% of the BOD get removed during the primary treatment. So remaining 70% of organic, that is in the form of colloidal or dissolved organic solids only, we go for the biological treatment. So the screening are used to any kind of a floatable matters like paper, cloths, any wood kind of a material. Then grit chamber is used to remove all the grit and sand particles, which is very high in specific gravity, around 2.65. So therefore, by reducing the velocity to some extent, we can remove all the grit particles. Then one of the important thing is to removal of oil and grease, because this oil and grease reduces the treatment. Okay, so biological decomposition. So therefore, we need to remove the oil and grease also using the skimmers. Then primary settling tank is used to settle all the heavy organic as well as inorganic solids. Then the next stage is a secondary treatment. So during the secondary treatment only, the remaining 65 to 70% of the organic matters, we can say it as a BOD. So remaining 65 to 70% of the BOD to be treated during the secondary treatment only. So during this treatment, we are converting all the thing into the stable byproducts. So mainly the treatment is happening here is aerobic and anaerobic. The aerobic and anaerobic bacteria contributing to decomposing the organic matters present in the sewage. So aerobic means we are using aerobic bacteria. So aerobic bacteria requires oxygen. So because of that, we are supplying the external oxygen in the form of surface or diffused aeration. And to maintain the MLSS concentration, that is as well as the organic loading rate, that is food to microorganism ratios. Okay, so we can achieve the very good efficiency of the removal of organic matters during the aerobic as well as the anaerobic treatment process. So therefore, the main treatment happening during the secondary treatment is a biological treatment. But in the primary treatment, is everything is a unit operation only. Screening, grit chamber, primary clarifier, all the three are unit operation. But here, the biological process comes under unit processes. Here, the bacteria decomposes the organic matters present in the sewage. So therefore, we need a biological unit as well as to settle down the biomass, we need a secondary clarifier also. So that's why in the primary treatment, we can call it as a primary clarifier. And in the secondary treatment, the sedimentation tank is called secondary clarifier. So therefore, the selection or treatment method is mainly depends upon the sewage characteristics as well as the effluent standards, that is disposal standards, and disposal facility where we are we are going to dispose our treated sewage. And in this particular treatment, we have a lot of developmental activities are going on, and we have a lot of proven, developed or advanced wastewater treatment techniques are available. It is some kind of modification of our activated sludge process. So activated sludge process is the one of the best way of treating our primarily treated sewage. that is best biological treatment system is a activated sludge process. In this particular activated sludge process, we have done a lot of modification like extended aeration or thorough mixing or fill and draw type or a different way of doing the aeration or a different way of using the bacteria. Yes, we have a lot of other treatment techniques are developed and we are using. So here the typical flow diagram of activated sludge process. So after the primary clarifier, the most of the settleable organic and inorganic solids are settled down. The organic colloidal and dissolved enter into the aeration tank. Here we are creating a very good environment to the bacteria. So that is, we are introducing air as well as the activated sludge. That is, we are maintaining the MLSS or and MLVSS, that is mixed liquor suspended solids or mixed liquor volatile suspended solids, and F/M ratio, food to microorganism ratio, or also called organic loading rate. So because of that, we are returning some activated sludge again into the aeration tank to maintain the F/M ratio as well as the MLSS concentration. And we are introducing the external air. So we are creating a better environment to the bacteria to decompose the organic matters present in the sewage. So at the end of this process, yes, we can achieve more than 95% of the organic matters removal. Then the active biomass is settled down in the secondary clarifier. So a part of active biomass is returned back to the aeration tank to maintain the F/M ratio as well as the MLSS concentration. And the excess part is wasted. Wasted means it moves to the sludge treatment. Okay, so sludge also we need to treat and safely dispose it. Okay, sludge from the primary clarifier as well as secondary clarifier, we need to treat and dispose it. Then here, after the secondary clarifier, the supernatant water is disinfected and we can dispose it based on the disposal facility. It may be any surface water body or any irrigation or any disposal into the ocean. So based on that, yes, the treatment facility also may vary, and we can choose the appropriate treatment facility. Here the aeration, that is activated sludge process, is a suspended growth process. So suspended growth means here the bacteria is in suspension. We are not using any filter media to grow the bacteria. So for that particular changes happening in the activated sludge process, that is, we are moving from suspended to attached growth process. It is not an advancement of activated sludge, it's a kind of way of treatment. That is, this one is the attached growth process. Here we are using the filter media. In that filter media, the bacteria is attached. The bacterial growth is happening over the filter media. When the raw sewage enter into the filter media, like this filter bed. Okay, so the filter bed having the filter media. In the filter media, the surface of the filter media, we have the bacteria attached. So when we are spraying the water, that is primarily clarified sewage or the filter media, so it contact with the bacteria attached in the filter media, and organic matters are decomposed by the bacteria. So therefore, it is a kind of attached growth process. So we can use any kind of rocks or any plastic media can be utilized. This particular trickling filter is also the aerobic process. Here also we are using the secondary clarifier to settle down after the trickling filter. So based on the raw sewage quality, we can recirculate. So based on the recirculation, we have a low rate, high rate trickling filters are available. Then one of the advancement of activated sludge process is a extended aeration process. In activated sludge process, we are doing 4 to 8 hours of aeration. But here in the extended aeration process, we go for up to 18 to 36 hours of aeration. So because of that, for the wastewater generation have very less quantity, like any institutions, wastewater from the any institutions. Yes, we go for the oxidation ditch because a very high detention time. We can handle the entire wastewater generated. So here we have the oval shape ditch along with the rotors. So rotor helps to do the aeration process as well as the mixing of that is avoiding any settling during the process, as well as it helps to maintain the velocity within the oxidation ditch. Okay, so so it is a completely mixed process. So because of the very high detention period, we can achieve more treatment efficiency than the aeration tank, that is activated sludge process. So it is a 1 to 1.5 meter depth oval shaped tank, maintaining the velocity of 0.3 to 0.6 meter per second. So it is a fill and draw type only. Once we reach the enough quantity, we have to close the inlet valve, and we have to do the aeration for next 18 to 36 hours. So once the biological treatment is over, we are open the inlet valve and allow the fresh sewage enter into the oxidation ditch. It removes the clarified water from the oxidation ditch to the outlet. For the small capacity of sewage treatment only, we go for this. That is less than 3,000 cubic meter per day quantity of sewage. Then another advancement in the activated sludge processes, sequencing batch reactor. This SBR techniques is used in one of the sewage treatment plant available in our Nesapakam sewage treatment plant. Okay, so one of the proven technology to get a very high efficiency of sewage treatment. So it's a fill and draw type. So the particular tank is acting as a equalization tank, aeration tank, as well as settling tank. So once we fill the sewage, so from the preliminary treatment, okay, so we can do the aeration for like activated sludge process. So we are introducing air also. So once the aeration period is over, we have to store the sewage to settle down all the sludge. Then the supernatant liquid water is removed and the sludge removed separately. So all these kind of processes are happening in a single tank. So therefore, it is a sequencing batch reactor. Then, so I already said we have both aerobic and anaerobic treatments. So far we have see some of the aerobic treatment. Then we have anaerobic treatment also. So one of the some important reactor we are using in some of the industries is UASB reactor, upflow anaerobic sludge blanket reactor. So we are introducing the sewage from the bottom. Here, bottom around 25% of the capacity is occupied by the sludge bed. Okay, so once the inlet sewage enter into the sludge bed, all the organic matters are get arrested here, and decomposition is anaerobic decomposition is happening here. So because of the anaerobic decomposition, carbon dioxide, methane, and other hydrogen sulfide gases are produced. These gases are moving towards the top. So during the time, the granular matter, that is sludge, also attached with some gaseous particle and moves to the top. So we have to split, we have to separate the granular particle from the gas. We have this baffle valve. So this particular top portion is called GLS. Top portion have the GLS separator, that is gas, liquid, and solid separator. Once it strikes the baffle, the gas particles are separated and it is collected in the dome structure. Then the granular particle gets settled down. If suppose it is escapes in this particular zone, this zone is acting as a settling zone. So therefore, all the suspended matters are settled down. So this kind of treatment facility is mostly adopted in some of the industries. Then we have the other treatment, advanced treatment like RBC, rotating biological contactor. So this is also aerobic system. So here we have the media pack containing the disc. So this disc is continuously rotating. When the disc is enter into the sewage, this disc contain bacteria medium. So whenever it enters into the sewage, the bacteria decomposes the organic matter and it comes out from the sewage. The aeration, because of the contact with the atmosphere, it gets the oxygen. So this is the way the RBC doing the treatment process. Then the final one is the moving bed biofilm reactor, MBBR. So here it is a suspended growth process. So along with in the aeration tank, we can introduce some plastic media also, suspended plastic suspended media. It is moving here and there. So it helps to grow the bacteria. The bacteria attached with the plastic media. So because of the suspended growth like aeration, the treatment is happening. The plastic media improves the efficiency of the treatment. And the MBR technology also available. So it is a membrane bioreactor. So after the secondary clarifier or sometimes aeration basin, we have the membrane process to remove all kind of suspended matters. It may be provided externally or internally along with the bioreactor. So up to this, I stop the presentation. So thank you for the listening. Is there any questions?
Sir, there are some questions in the chat box, sir. So in a desalination process, whether ions are recovered from water? And in the same process, is there any changes in major and minor ions happen in water?
Yes, yes, we can separate the ions, but mostly these are all the rejects from the thermal process as well as the membrane process. Handling of those rejects alone a huge topic. In defluoridization process, is there any changes in major and minor ions happening? Yes, we are adding alum and lime. So therefore, hardness also get removed, and it increases the removal of colloidal solids also.
So, participants, if you have any doubts, can unmute your mic and ask. So, there is no doubt. So, the attendance link is being shared in the chat box. So, I request participants to fill the attendance. So, attendance will be posted at the end of each session. So, we are supposed to fill the attendance. Okay.